Okay, what we've done so far with work and kinetic energy is nice. It's and it's moderately useful for solving some problems. But in fact, we can make it a lot more useful. And one of the best ways to make it useful is to introduce the notion of potential energy, which I'm going to do here. So let's start with what we know. What we know is that the change in kinetic energy is equal to the work done by any forces which are doing work in the problem. So what I'm going to do now is I'm going to take this work and I'm going to move it to the other side of the equation. So now we have K2 minus K1, the change in kinetic energy, minus the work done is equal to 0. Okay, that's just simple algebra. And now suppose, just suppose, that the work done depends not on how you get from the first position to the second position, but simply where the first position and second position are. In other words, suppose that we can write minus W in the form U2 minus U1, where U2 is a function that depends only on where the particle ended up, and U1 is a function which depends only on where you started. If you then do a little bit of algebra, you will find that the K2 minus K1 plus the quantity U2 minus U1, we rewrite that as K2 plus U2 minus K1 plus U1, and we rewrite that as E2 minus E1 equals 0, where E is defined to be K plus U. U is called the potential energy, and E is called the total energy. So you see we now have sort of redefined energy here as the energy is equal to the kinetic energy of the object plus the potential energy of the object, where the potential energy is introduced as we did up here. Okay, so now what we have is we have that the change in the total energy of the system is equal to 0. Now this is an equation which is extremely useful in physics. Physicists are always looking for equations of this sort, and if you think about it a minute, what this equation says is that under the proper conditions, we find a quantity which never changes. This is called a conservation law. Okay, so the change in the total energy of a system, if we introduce the potential energy for the forces which are acting, is equal to 0. Now the catch is that there are some forces in nature for which, and we'll talk about this later, for which the work cannot be written only as a function of where you start and where you end. It will depend on how you got there. But many forces, which are called conservative forces, many forces in nature, the work that they do only depends on the endpoints. And so if you find that that's the situation for a problem that you're doing, and we're going to do several examples of this kind of potential energy, then you have a situation where the energy will be conserved. So here is the important thing to remember here. The energy is conserved for any system where there are no external forces doing work. Notice that it doesn't say there are no external forces. It says there are no external forces doing work. And some of the examples that we do, there are going to be external forces, but they won't do any work. So what external forces means are one of two things. First of all, it means some force which is, as the word implies, external to the system. So if you're watching a system, a block sliding on a tabletop, for example, okay, there will be external forces on it. There will be its weight. There will be a normal force. There might or might not be a frictional force. There might be a string which is acting, pulling on it. Those are all external forces. If those external forces do work, then energy won't be conserved. The other kind of force, which is what we mean by an external force, is any force for which you have introduced a potential energy. Now, so far we haven't found any potential energies. That will be the next video here. But if there's only one force doing work in a particular problem, then if you can introduce a potential energy function for it, then the total energy of that system will be conserved if there are no other external forces. Now, I've often told my students in the past that one way you can look at potential energy is simply that it is a bookkeeping device which automatically calculates the work done by some force in a problem which is always there. For example, if we have an object which is moving around in a vertical direction, say a projectile or a stone dropped off a bridge or something like that, there is a force which is always there, which is the object's own weight. And if we can figure out what the appropriate potential energy function is for the weight of an object, then we can simplify lots and lots of problems. Okay, that's going to be the next video, figuring out what is the potential energy for the gravitational force.